Welcome to Chapter 7, Sedimentary Rocks, for Go Give It Community College Geology class. Also, before I get going, if you have questions, the chat window is disappearing on me, so raise your hand if you type in the chat, and I'll go look at the chat at that point. Just wanted to get that out there. So, sedimentary rocks. We talked about igneous rocks already, talked a bit about erosion and weathering. That falls into sedimentary rocks. Rocks that are formed on or near the Earth's surface is how we define them as sedimentary. Since sedimentary rocks are the rocks on the Earth's surface, the vast majority of the Earth's surface is sedimentary rocks, right? That kind of makes sense. Those combine. That being said, sedimentary rocks are definitely not the most common type of rock. By volume, they only make about 5% of the Earth's outer 10 miles. The top of the Earth is covered with sedimentary rocks. Beyond that, you don't have them anymore, again, because by definition, sedimentary rocks are formed at or near the Earth's surface. Sedimentary rocks show evidence of past environments. We'll get into that. And they contain most of our important natural resources: coal, oil, natural gas, groundwater, etc., etc. Kind of makes sense since the majority of the Earth's surface is sedimentary rocks. There we go. Couple of definitions for you. A sedimentary rock is essentially a glued together cohesive collection of fragments and crystals that are found on the Earth. Or another way to say that is a sedimentary rock is a cohesive collection of sediment. The loose material on the Earth would be sediment. That would be your gravels, your soils, your sands, things along that nature. Anything that's loose and disheveled around, we consider as sediment. Pack them together in some way, shape, or form so they form a hard rock, you get a sedimentary rock. Sedimentary rocks are the products of mechanical and chemical weathering, which we discussed last chapter. You can move the sediments with the erosion. You break them down with the weathering, both mechanical and chemical. And as this deposition continues to grow, as you break down old rocks, move them around, put them into places, they eventually come together, or the geology term for that is lithify. Loose sediments are lithified into cohesive sedimentary rocks. Lithification is can be a somewhat complicated process, but it is not unfair to say that it is a gluing together of the rocks. There are three main types of sedimentary rocks: detrital, chemical, and organic. And we'll go over those three examples. Detrital, we're going to define as that base gluing or cementing together of various fragments and sediments. Chemical and organic sedimentary rocks are a more complicated approach, and I'm sure you can gather from the definition, chemical and organic sedimentary rocks involve some chemistry or some organic component to them. Here are some nice charts explaining a few of the different rock types and some of the examples and some definitions we can use to go along with them. On the left here, we have detrital sedimentary rocks, and we can see that you have different particle sizes associated with that. And those particle sizes, as we'll get to, essentially defines how fine the rock is. If the rock is made of big chunks, you probably have a lot of gravels involved. Call that conglomerate. If the rock sizes get smaller and smaller, you get your sandstones, your siltstones, your shales. That's a primary way to decipher them. Chemical and organic rocks, conversely, don't all form in that same cementing, that same gluing together process that detrital happens. So we need to get more complicated about it. Different compositions, varying textures, etc., etc. This goes better with pictures, as you would imagine. So we're going to move on to that. When I say sediments, what do I refer to? Well, a sediment, as said before, is by definition any loose fabric on the Earth, but usually the sediments would include clays, quartzes, feldspars, micas, and other various chunks and pieces of rock. Those four, clay, quartz, feldspar, mica, will sound familiar because they're minerals. Those are very basic geology foundational elements. And when you glue them all together and you cement and lithify them together in some way, shape, or form, you get a sedimentary rock. You can describe the rock and all these sediments and how they go together is your definition of most detrital rocks. Describe particles by sorting and shaping, as said there. We describe sorting as in from poorly sorted to well sorted, essentially how many of the pieces are of the same size. If you get rocks that are more or less all uniform in size, you could say it's well sorted, right? This the way you would sort anything else in your day-to-day life is the same way geology is sorted, because as I said at the beginning, geology is a very nice science, and that a lot of the definitions and terms it uses are everyday terms, and they mean more or less the same thing. A poorly sorted sediment is a lot of different sizes and shapes and configurations of sediment, and it goes up to well and very well sorted. Rounding or the sphericity or the angularity of the rock again refers to exactly what you think it would. A rock that is very rounded is round. A rock that is very spherical is a sphere. You can't, these are not, as shown here, linked definitions. You could have a very angular rock that's also very spherical, and you could have a very smooth rock that is not spherical at all, right? Sphere is the shape, the angularity is the roughness around it. And as we get into more about this stuff, you'll see how these sediments form. And the good thing about geology is we can see sediments form in this way in our day-to-day lives, and that tells us something. If we see a rock that's old that has these same characteristics to it, we can infer things about the way that rock formed. Pictures shown here. This is another thing where this as an in class is nice because you can look at these, but the size and the shape of the rock dictates what we call it. A conglomerate or a breccia is essentially a bunch of big pieces all glued together, almost kind of concrete or cement looking, right? Very common rocks. And the difference between conglomerate and breccia, I'm sure you can tell by looking at them, is the angularity. Breccias have very sharp angles. Conglomerates tend to be rather smooth. If you get the size of the particle down from being what most people would assume as a rock to being more of a sand, you get sandstone, most obvious name on the planet, right? And then if you get past sandstone, where you lose that, again, sandy texture, and you get to something that's still made of sediments, but is probably too fine to feel like sand, for example, a mud, you get your shales and your mudstones and siltstones. These are all the same mechanism. It's just a question of what is being cemented together, what is being lithified. Shale, as shown here, is essentially the soft, muddy bottom of a water source, such as a lake or something along those lines. Very tiny, fine particles falling down into layers creates something that looks like a rock made of mud, because it is a rock made of mud. Very common sedimentary rock, because again, it's the lake bottom, the sea bottom, something along those lines, and that's very common throughout the world, right? Very tiny grains, varies in color depending on, again, sedimentary rocks are rocks formed usually via the destruction of other rocks and minerals. So the color and the texture of the shale very much is dependent on whatever was falling in that lake bed to form shale. A mudstone or a siltstone, essentially the same thing. It's just a grain size difference. 9 times out of 10, if you see something super fine grain like that and you call it a shale, no one's going to question you on it. But technically, there is a difference. Siltstone, as shown here, big difference between a siltstone and a shale is layering. That has that little stacked pancake look to it to shale. Mudstone, siltstones don't. But as said before, if you call these three are more or less interchangeable, they're not interchangeable, but mostly people don't care unless you're hard, deep in geology, any of these very super fine-grained rocks, you want to call them a mudstone. That works because they're essentially muds. Sandstone is exactly what you think it is. It's a rock that's made up of sand. Zoom in on a sandstone, you see little particles of sand. Those little particles are usually quartz. Quartz sandstone is very predominant. If you live around the Houghton branch of the GCC campus, you're going to know a lot of Jacobsville. It's a very bright, vibrant red sandstone that we have up here, but sandstone's everywhere because it comes from sand. Where does sand form? On beaches. So if you find sandstone, that means you essentially are sitting on what was once a beach. Right, there's the Jacobsville I was talking about before, that vibrant reds and whites, actually somewhat rare in terms of sandstones throughout the world, and of course, very beautiful. More pictures, here's some pictured rocks, pictured that way because they're just gorgeous looking sandstones, right? And that's the fun part, is this sandstone is comprised of sand. We find sand, as I said, in beach environments. So you know when this sandstone, before it was formed, that was sand sitting in this exact location. Things come together. Quartz sandstones vary wildly in color, again, depending on whatever formed them, whatever made them. Acros is a variant of sandstone that has a lot more feldspar in it than quartz. Grains tend to be a bit larger. Again, this is sort of a shale siltstone conversation, wherein if you call this a sandstone, only someone that's really good at geology is going to correct you on that. And for the most part, it's kind of an irrelevant conversation because the process is still the same. Greywacky, a less common variant of sandstone, is, again, a sandstone, but the sediment that was used to form it is different. Greywacky has a lot of grays involved in it, and oddly enough, Greywacky tends to have big chunks of random stuff in it, as shown in this picture. The sort of a definition of Greywacky is it contains rock fragments. You wouldn't expect that to be a definition, but it's just a very common occurrence for that particular sandstone. Finally, we get to conglomerates and breccias. These are, if your rocks, as I said before, get big enough to where they're not sand anymore, but you actually get chunks of gravel that look like they're cemented together, not unlike cement or concrete. You get these, and the defining difference between them is one is rounded and one is not, as shown here. Conglomerates are still very common, and this, of course, where are you going to find a mixture in our day-to-day life of large and small rocks? Well, maybe you have a bit of motion to the water flow. Maybe a river or something like that is going to have this mixture. Well, then conglomerates must exist now where some amount of flow to the water happened. Again, that's the cool part about the sort of geology. Here we have a breccia because you have these nice angular stones that were cemented together instead of the rounded ones. What does that say? Well, the more something tumbles, the more something smooths, right? A angular fragment says the rock didn't tumble very much before it was lithified. Geology is so nice in the fact that the more you look at the world around you, the more you intuitively understand geology. There isn't many tricks involved. You look at a bed such as this, and it looks like a big mixture of rocks, probably because this is an old riverbed, a mixture of rocks, different shapes and sizes, with a decent amount of angularity in some of them. Fast forward a few, tens of thousands of years, this is going to solidify into a hard rock. The two look the same because the two are the same, right? The distinction between conglomerate and breccia is there is like a strict definition to it, but if you think the rocks look more round than they do angular, call it a conglomerate. I'd probably call it a conglomerate because those rocks look round to me, right? And as said previously before, these different layers indicate different fluvial environments, different places where the water has existed. So if you have sandstone at the top there and then poorly cemented shale underneath, What happened here? Well, that shale, that layer of shale is when you were at the river bed, the lake bed, and then the lake receded, moved, and you started depositing sandstone on top of it. This is the tectonic process, the erosion, the weathering process that happens in our day-to-day life. Remember, these two layers originally were completely on top of each other. Erosion has wiped stuff away. So this is essentially, you're looking at a snapshot of history of some sort of water system moving and changing its location. Because sandstone is a beach, shale is a lake bed. That's your classic, your detrital rocks, your simple cementing, gluing together of different fragments. We can get to chemical rocks now. Chemical sedimentary rocks are formed from the precipitated material that was once in solution. If you go back to your high school chemistry class, what is a precipitate? A precipitate is something that comes out of the mixture of different chemicals. If you mix two different liquids together and a solid falls out, you call that solid the precipitate. Likewise, if you mix different chemicals and a gas comes out, that gas would also be the precipitate. It's the chemical reaction that goes on, hence chemical sedimentary rocks. Precipitates can occur by inorganic processes such as evaporation, or organic processes such as water-dwelling organisms. Again, shown here, chemical and organic rocks. The chemistry involved and the way it worked together gives you different rock types. If you have calcite, CaCO3, as your main chemical, the way in which that calcite originated defines your rock, be it a travertine, a coquina, a fossiliferous limestone, or a chalk. If you have, for example, quartz formed as a precipitate out of X, Y, or Z various thing in the past, you get your chert, jaspers, and agates. Gypsum, halite, and of course coal all come in these exact same formats. It's not the gluing together different parts, whether it's the mixture of different chemicals and what results from those mixtures. Limestone, we've all seen limestone, very abundant, right? It's essentially the result of organic and biochemical mixtures to produce calcite, and that calcite solidifies. If you have fossils that are called fossiliferous limestone, sort of just a location definition more so than anything else. But that's the process, right? Is fossiliferous limestone. We see a lot of seashells here. So that tells us we're probably at some place where seashells exist, such as a bottom of a sea, right? And this limestone precipitated because the creatures that created the seashell were extruding out calcite, and that calcite was growing, stacking over time, becoming solidified, becoming together. We see sea life, such as mollusks and seashells, do this on a day-to-day basis. Limestone is being formed every single day via the same process that was formed 5 million years ago. Crystalline limestone would be something as an inorganic combination. When chemical changes increase from calcium carbonate, the content of the water, that calcium carbonate eventually precipitates out, forming this limestone. If you don't see a lot of fossils, if you don't see fossils involved in the process, such as what's shown here or here, you have a crystalline limestone. Exact same stuff going on, just instead of a creature spraying out calcite, you have the nature and the combination of whatever's going on in that particular, usually fluvial water environment, precipitating out this substance. Coral reefs, of course, would be an example of this. If you have, because coral reefs are made up of a lot of calcite, and that's the cool thing, is we can look at this Great Barrier Reef and we can say, oh, look at that. That has a very specific definition to it. And you can go to the Guadalupe Mountains in Texas and you see a lot of these exact same signs and markers. Well, maybe this current mountain range in the middle of dry, arid Texas, there was once a reef here because these two look very, very similar. I have no reason to assume they're different. So Texas was once had a giant reef at it. Limestone, again, same song and dance. This limestone was formed via inorganic or organic means. You could tell the difference based on if you sea fossils and stuff. Travertine. This is another variation of this exact same process. This forms of chemical changes increase the calcium carbonate in the water again until it precipitates. This travertine, for example, here was formed when water entered the cave and carbon dioxide pushed out. Kind of going over the same song and dance as the previous ones. Something causes the calcite, the calcium carbonate, to leave whatever is holding it in place. That calcium carbonate settles down, compacts. Coquina is a weird rock. Coquina is a weird rock because it is essentially a detrital rock, a squished together bunch of components, but it's squished together via calcite means, so we kind of call it a chemical rock. And it is essentially, it is 100%, I'm not going to say essentially, it's 100% glued, squished together shell fragments. This would probably be because the environment in which the shells formed wasn't under enough water for that calcium to accrue around it to give you that fossiliferous limestone. Instead, the calcium kind of wasn't able to build up as much. So instead of building the limestone around it, it just cemented these shells together. Right. And again, you look at these two and I ask you, what do you think the difference is? Well, one built up the limestone, the other one did not. And finally, we can get to chalk. Chalk is a smaller version of what we've been seeing. It's the same chemical involved, just instead of, let's say, mollusks and shells producing it, you have plankton. Coccolithophores down here in this electron microscope. These tiny little individual microbe-sized almost plankton that release this calcium carbonate, which eventually forms a limestone-like rock. Just we call it chalk because it's different looking from limestone. And instead of, again, the mollusks or some sort of chemical weathering going on to produce the rock, we have this association. And those little tiny plankton release this calcium carbonate over time, building up massive layers of chalk. The white chalk cliffs, as shown here, the White Cliffs of Dover, very famous, all through this process. Cool. Let's move on away from calcium carbonates and go into quartzes, such as chert. Chert is the same process that we talked about with limestone, just instead of CaCO3 coming out, it's SiO2. It is quartz precipitated out of whatever is causing that to arrive. And then from chert, you get your flints, your jaspers, and your agates, which are all essentially variations on a theme here. In the same way that sandstones can be all those different colors, cherts can be all these different colors, depending on the origin of the silicone. Agates are very popular around the Gilbert Community Campus, Gilbert Community College campuses. I'm sure you've went to agate hunting at some point with your parents, right? You probably still do it. They're very pretty rocks. And the difference between agate, flint, jasper, petrified wood, technically, is the origin of the process of how they were formed. Other examples we can talk about halite, we talk about salt, we talk about that as a mineral. If you get a lot of halite bunched up together in a location, a lot of halite precipitated out of, say, salt water, when the salt water evaporates instead of went someplace else, you can get yourself gypsum and rock salt. And rock salt is a rock that is salt. Geology is nice in that way, right? You could tell a rock salt is rock salt because it tastes like salt. The difference between rock salt and halite, the difference between the rock and the mineral is just the crystal itself, whereas rock salt and rock gypsum are a rock composed of many of those different crystals cemented and lithified together. If you just have the crystal itself, you have halite. If you have, for example, this rock salt up here, that's not one crystal. That is a bunch of crystals all stuck together. This is your definitional difference. Sedimentary rocks are cemented, glued together in some way, shape, or form, chunks of other stuff, be it fossils and calcite with your limestones, be it sand with your sandstone, be it rock, salt with your halite and gypsum. Cool. Those are more or less inorganic processes. We could talk about organic processes, essentially the pushed together parts of organic material that's been lithified. When I say organic material, I mean coal. Coal in its various forms, such as peat, lignite, bituminous, and anthracite, are all these squished together remains of dead carbon-based material. Coal is carbon. We burn coal in the same way we burn wood because it's the same chemical material. Your plants form. You've heard the story of coal before, I'm sure, in high school or middle school. The plant forms. It starts to decompose. It solidifies together to form peat, which essentially is has the consistency of dried poop because that's basically what it is. As that peat compacts down and squishes, you get lignite, which is a mid-process to bituminous, which is your useful coal. And then if you keep squishing that coal more and more, you get anthracite, which is technically a metamorphic rock. We'll get to that next chapter. And yeah, just keep squishing that dead plant matter together, and it gets coalier and coalier and coalier. So let's talk some of the changes that can occur to sediment after you deposit it, after you form it. Diagenesis is the term we use to describe the chemical, physical, and biological changes that take place after sediments have been deposited or buried. The genesis, of course, would be the formation of the stuff. The diagenesis is the alteration within it, usually happening, of course, within the first few kilometers of the Earth's crust. If you get too deep, things start to melt. You get metamorphism or igneous formation. Recrystallization is an example of this, changes of aragonite to calcite. We talk about stuff like that. And of course, the example I just gave you of the coals changing is diagenesis of peat to lignite, and of lignite to bituminous, and of bituminous to anthracite. To turn these changes happen through lithification. I talked about this before. The lithification is the unconsolidated sediments that are compacting and cementing in to form the rock we talked about. Compaction happens via burial, via pressure, and kind of how it sounds, squish stuff together. Where do you think you get sandstone from? Because you squished a bunch of sand together. We've all made those like soft rocks at the beach by picking up a bunch of wet sand, forming it in our hands, and it holds its shape for a bit, right? Instead of your hands doing that, imagine the weight of a continent. And you get the same idea here, right? And cementation involves some sort of gluing together beyond just the simple squishing of the rock. What that glue is, we don't get into that too much, but that's a conversation we had in a class that's more dedicated to sedimentary rocks. As I showed before, the compaction and cementation, these pictures describe essentially what I was talking about. Take a bunch of sediment, a bunch of particulate matter, squish together real hard, get yourself a sandstone, or if you want, you can cement it via X, Y, or Z glue means to get yourself a conglomerate. The parts that are not the big rocks of the conglomerate are the glue that's holding them together. And if you are able to chisel at it, you can break off those big rocks. So I've been perusing over this base concept here, but sedimentary rocks are very good examples of the present is the key to the past of the idea of uniformitarianism, meaning we can watch these processes go down in our day-to-day lives, and then we can infer that, oh, look, the bottom of this riverbed is, the bottom of this lake bed is all mud, all very fine sediment layering on top of itself. I have this rock over here that's very fine mud-like sediments that looks like it's in layers. Maybe the two are connected. As was said before, these rocks and where they form and why they form and how they form depends a lot on the environment of their deposition, of their formation. In very broad terms, we can talk about three different sedimentary environments: continental environments, marine environments, and transitional environments. I'll go over these, but you know what they are by their names, right? What is a continental environment? Well, it would be an environment on the continent, right? What's on continents? Well, streams, lakes, stuff like that. You get a deposition that looks like it's from a stream. It was probably from a stream. Glacial deposits work in the same way, mixing sediment around, getting boulders pushed around, digging out lakes, such as the Great Lakes that we have around us. And of course, wind can also do this work. You see rock that looks like it was once a sand dune. That's probably because it was once a sand dune. Marine environments would be, of course, your deep lakes, your seas, your oceans. These are marine environments, be they shallow or deep. Since these environments are different in the way that in regards to the sediment and the creatures involved, they also are different with respect to the rocks that are eventually developed from these environments. Shallow marines are, just shallow part of the lake or the river, the ocean. Usually we say about 200 meters deep. Receive lots of sediments from lakes and the abundant sea life, what have you, usually very warm, minimal sediments, very carbonate rich, things along those lines. Once you get into your deep sediments, you get your deep marine, you get your fine sediment accumulation on the ocean floor. Again, because we can know these things are true because they're happening in our day-to-day lives. And we have no reason to doubt that the way oceans work now is different from the way oceans worked 500 million years ago in terms of mud. If we find a reason for that to be different, we can reassess what we're talking about here. A transitional zone would be between continent and marine, beaches, lagoons, deltas, what have you. This picture zooms in a whole lot on all these different conversations, but it is more or less working the way you think it works. Your continental zone would be up into the mountain. Your transitional zone would be your beach, your estuary, your delta, and then your marine zone would be your waterways, your deep sea fans, things along those lines, right? You've probably seen these sort of pictures before. This is not very difficult to comprehend. Or what's the difference between a shallow marine and a deep lake? Well, probably not a whole lot, actually, except for size, right? Lake Superior, for example, is very, very deep. So there probably is a lot of connection between a shallow marine environment and, say, the ocean and Lake Superior at certain points. Beaches are beaches. If you live up around the Go Give It Community College campuses, you're probably used to rock beaches, as shown on the left here. But sand beaches do exist, and they are fun to visit. I suggested doing it at some point in your life. Tidal flats, lagoons, all the same conversation, right? A beach and a lagoon or a beach and a tidal flat are different environments and produce different results accordingly. And if we notice the way they're different nowadays, we can look back in time and find the rocks associated with these different locations. Glacial deposits happen from glaciers. You find a rock that you're like, this doesn't make much sense. Why is it here? And you can look back in history and say, oh, hey, I have this very large glacier-sized deposit shaped like a glacier. Maybe it's from a glacier, right? And if you're in a particular part of the world that you don't think had glacial activity, you don't find glacial deposits. What does a glacier do? I'm sure we're all aware. It bulldozes its way into wherever it wants to go. What happens in front of a glacier bulldozer? Churning, mixing, unsorting of the rocks. Swamps and bogs, that's going to be coal in a few million years. Right? Very, very full of carbon, very full of plant and animal matter. It's probably not going to go anywhere for a while. Lots of very quiet dropping of mud dunes in the shale. Coal and shale always found together. Stuff makes sense. Streams, you can know a stream because what does a stream do? How does a stream differentiate itself from, say, a lake bed? Well, streams move. When streams move, rocks tumble around. You get the faster the stream moves, the more the rocks tumble. The more the rock tumbles, the less angular it gets. Geology is wonderful in that way because it works exactly as you think it works. What is a landslide? Well, that's a big unsorted jumble of many different sediment sizes. We can find the evidence of landslides in the geologic record. Coral reefs, talked about that already. Coral reefs essentially nowadays are big limestone structures in shallow, calm environments. So if we see big limestone structures in shallow, calm environments that stick up like this, find ancient coral reef, especially if we find the fossils associated with it. So yes, as I said before, these sedimentary structures provide useful information for the interpretation of the Earth's history. The type of sedimentary structures we talk about include strata, or you're probably going to refer to it best as bedding. What is strata? Well, that's the layers of the rock we looked at. I talked about before, the difference between a shale and a siltstone is the shale has layers. It looks like there's different beds of rock, different little horizontal sections of rock that were laid on top of each other. Sounds like, stacking a bunch of mattresses, stacking a bunch of beds on top of each other. Same process. We can watch this bedding occur, and we can see interesting things happen because of it. I talked about this a bit in chapter 1, but we have a cool example of something called cross bedding, wherein these different layers, those lines of sediment, intersect with each other and move around. And sometimes they cut each other off, such as the bottom there, that truncated bed. Sometimes they bend and shapes and they have cracks and holes in them. And these are examples of something affecting the sediment before it solidified. What could have done this? Well, lucky for us, we can look at a sand dune, such as that insert picture, a small picture in the left, and we can see this cross bedding occurring, more or less. Nowadays, we have this in the left, and we find solidified old rock on the right. It looks like this. Well, maybe the two are connected in some way, right? Here we have ripple marks, they're called, small waves, essentially, shown the rocks. What makes small waves nowadays? Maybe the same thing. This rock looks like it's cracked up mud, like a dried up mud puddle. Maybe there's a connection there, right? And of course, we can talk about coal. Coal is a commonly used fossil fuel. It's called a fossil fuel because it's made up of the fossils, right? Squished together swamps and lagoons and what have you. Lucky for us, coal more or less is becoming less prominently used because it's very polluting. But coal is also a good source of energy. Bituminous anthracite coal shown down there. Lots of BTUs per pound, British thermal units, but you can kind of burn any coal you want, to be honest. You're not going to get as much energy out of it when it's less compacted. Oil and natural gas follow the same process. Oil is derived from the remains of marine plants and animals. Different hydrocarbon association there, but it's a similar process of formation. Why do you get coal in some places and oil in other places? I'm not going to go too deep into that, but you can probably imagine different depositional environments create different things, as we talked about before. Why are all these different variations of limestone, of calcite throughout the world? Why do we have limestone, chalk, what have you? Because different depositional environments, different reasons and locations where they're buried, what they're buried around, what have you. Oil, natural gas, same process. Actually, natural gas is a derivative of oil. It's not really a separate thing. If you ever get the opportunity to look into all the byproducts of oil, kerosene, gasoline, what have you, it's very interesting. So this is common oil traps. An oil trap is essentially something that, the name gives it away, traps oil. Oil is found in specific pockets of the world, and it's essentially like oil's a liquid. Even down in the bottom of the world, in the bottom of the crust, down deep, oil's still in a liquid form. It's the reason why the oil is stuck there is because it's been trapped by the surrounding geology. Oil is technically more common than what we find, but if the oil isn't trapped, it spreads throughout and becomes too weak to be usable, right? If the oil is somehow encased in its surroundings via some cap rocks, a salt dome, an anticline, pinch out traps, what have you. We can harness it, we can use it, we can drive our cars around. Of course, there's a lot more to this conversation than what I'm going over. Feel free to look into it more in depth yourself if you want. If you know someone that has an oil platform on their property, hey, go check it out. It's cool stuff, right? And the geology surrounding oil platforms is very fun and interesting. As said before, I'm going to go through these real quick just so you can take a look at this slides in the YouTube video. If you want to pause at any point and spend more time on these, you can. Get to understand how this stuff works. I will stop the recording of the video. If you have any questions on any of this information, we can have that conversation. Thanks for watching.